Hello, today we'll be learning about vectorization, a technique widely used in modern computers to increase the efficiency of operations on vectors, the name given to one-dimensional array data structures. Most scientific computing applications rely on repeated integer and floating point computation on arrays. Exploiting the structure of these operations can increase the throughput of the application, enabling the scientists to do more science. Therefore, it makes sense to think of ways to speed up these processes. Eventually, we can generalize all these ideas to matrices or tensors. This is something particularly of use for machine learning and linear algebra today. Let's begin with a simple overview of what we mean by vectors and vectorization. We will first review a simple vector operation computed sequentially and how this is implemented. We will then suggest how we may be able to increase the throughput of these computations by modifying our machine architecture. With this new machine architecture, we'll look at how these modifications impact simple implementation of our vector operation in the C programming language. Our changed architecture relates to concepts you might have explored before, such as caching, and so we will discuss briefly the benefits and restrictions of our new hardware. We will also discuss the history of hardware support for vectorization to understand how these methods may continue to develop. Finally, we will discuss how you can write your software to benefit from the increased efficiency of vectorization. Vectorization relies on the SIMD hardware paradigm from Flynn's taxonomy. The approach is to explicitly perform a single instruction acting simultaneously on multiple data. To motivate the subject of vectorization, let's start with a simple addition of vectors x and y, both of which consist of n elements. Save the output of the addition into the vector f. Therefore, on an element-by-element basis, we add x0 and y0 together and store the outcome in f0. Likewise, we do the same with x1 and y1, etc., as we iterate through the vector's n elements. This means that our arithmetic logic unit is reading in two pieces of data and performs the addition of them one pair of elements at a time. So, the motivation for thinking and talking about vectorization comes from asking ourselves the question, can we think of redesigning our machine to make this process faster? To dive deeper, recall that a processing unit consists of several components. A processor has, for example, a controller or control unit and arithmetic logic units or ALUs, which perform the actual computations. There are other components as well, but let's just focus on these two for now. Now imagine our controller as a puppet master, which tells the ALUs what to do. We could also imagine this controller handing out orders to more than a single ALU instead. It could coordinate, for example, two ALUs both carrying out the same operations. If we think back to the working at a desk analogy, we have one ALU sat at a desk. It can fit two sheets of paper or two pieces of data on that desk. That is the data in which the ALU acts on. The sheets of paper are analogous to the computer's registers. We can't fit more than two sheets of paper on a desk, but we could use two separate desks with an individual worker on each desk. So with our two ALUs, one at each desk with two sheets of paper, we now have four registers and two ALUs to act on this data simultaneously. This principle defines our new machine. We'll consider vectorization in the context of a long-running loop. We loop over each element of an n vector, x, or an array with n elements, and an n vector, y, and add corresponding elements together to store the result in a final n vector, f. Computationally, for very large n, this can be a significant computation, and this process, running on the von Neumann architecture, is not effectively using the computational hardware. We must perform 3 memory operations and 2 unrelated integer calculations for every iteration of this loop. Now we're able to think through the steps of the operation for the simple vector addition on our new machine. One ALU loads x0 and y0, while simultaneously the other ALU loads x1 and y1. Each ALU is then given the instruction from the controller that they must add the contents of their registers and store this result. One ALU writes f0 equals x0 plus y0, while the other writes f1 equals x1 plus y1. Since these are independent calculations with identical structure, they may proceed at the same time and at the same pace. Ultimately, we have completed several instructions, with each ALU having performed its own operations during the same time it would take a single operation to complete. Vectorization applies these techniques to general problems using larger vectors in dedicated registers alongside specialized operations. And you can hopefully now visualize how this process can increase the instructions per compute step, particularly for vectors, hence the name. Now that we have our analogy for vectorization, it is crucial to see this concretely in a simple C program. We again consider our element-wise sum of two vectors in a loop. Each iteration step of our old machine would 1. Load xn and yn into registers, 2. Perform the addition, 3. Store the result in another register and save their sum to fn, and then 4. Increment the counter if it has not reached the maximum m. If not, we go back to the beginning of the loop and work through the next iteration until we hit the maximum step count. For a vectorized loop on our machine with two ALUs, we again compute the addition of xn and yn to save to fn, but we simultaneously also compute the addition of xn plus 1 and yn plus 1 to save into fn plus 1. In this case, the iteration counter must be incremented by 2 at each step. As with the old machine, we then check the iteration counter against the maximum and restart the loop if the maximum has not been reached. This is sometimes referred to as an unrolled loop, here with an unrolling factor of 2. Therefore, on each iteration of the unrolled loop, we have computed twice as many additions as the original loop, with performing the same number of memory moves and doing half as many iterations overall. In practice, vectorization is carried out by the compiler, which needs to recognize that the code is vectorizable, meaning that it can translate code to vector instructions. Note that on the hardware level, vector instructions are different from the regular scalar instructions, as they make use of specialized ALUs for vector operations. Our simple vector addition example allows us to see how, for each iteration of the loop, there are twice the number of operations being carried. So some keywords which are frequently associated with vectorization performance are throughput and efficiency. In the context of vectorized computations, by throughput we mean in a very general sense the amount of processing being done per unit time, whether that be in a second or per CPU cycle. If we can process 2 floating point computations in the same tick as one, this would mean an increase in the throughput by a factor of 2. On modern hardware, vectorization capabilities make factors of 2, 4, and 8 readily accessible. On the other hand, efficiency is a measure for how effectively we are utilizing the hardware capabilities. If our hardware is capable of processing 4 floating point operations per cycle, but our throughput is only 3 per cycle, that would correspond to an efficiency of 75%. The efficiency of a calculation can sometimes be a more subtle thing than it first appears. If the calculation does not map onto the hardware capabilities easily, it can be challenging to estimate theoretical peak performance. Having discussed the principles of vectorization, let's talk about vector hardware now. Vectorized operations are carried out by vector compute units. These are specialized hardware able to perform the vector operations we've talked about so far, and are different from regular ALUs, which in this context are often called scalar processing units. The vector processing unit saves some silicon because the control logic is only required once, while twice the compute logic and hence twice the throughput can be allocated. The physical realization of these vector compute units is different to our schematic of the 2 desks. In the hardware, we have larger registers that can store multiple values of our typical data types. This works nicely for operations with regular access patterns, such as a scalar product, but for computations with branching control flow, for example an if statement, then the compiler is frequently unable to vectorize automatically, as it cannot prove that the transformation is valid. Modern approaches to vectorization will use techniques like masking, i.e. the use of an auxiliary bit per element to indicate inclusion or exclusion from the computation. Sometimes compilers can deduce that a piece of code may be vectorizable by means of masking, and will automatically vectorize your code for you. But more often than we'd like, the compiler won't be able to reliably do so if the logic becomes too complex for it to handle. In that case, you can help the compiler by implementing the masking manually yourself. Hence, for vectorization to be implemented efficiently, the best case is that the data is stored contiguously in memory. This is simple for arrays in C and Fortran. In a vector X, the elements x0 and x1 are stored next to each other. If we load x0, there's a high probability that x1 is loaded within the same cache line. We refer to this as coalesced memory accesses. Further to that, we can dump the whole cache line in one rush into a large vector register. Whereas, if element A is stored in one location of memory and element U is stored elsewhere, then the load of A is uncorrelated with the location of U, and loading both will be slower than if they were the first and second elements of an array. The latter can be conceptualized as a vectorized load instead of a scattered load for A and U, for which there is an analogous vectorized store. The implementation of vectorization in hardware is old, and the legacy of vectorization is still influencing the development of hardware today. Vectorization was first introduced by Cray in their so-called vector machines, beginning with the famous Cray 1 in 1976. However, these machines were expensive, and because they were designed specifically for vector computations, they struggled at more general-purpose computation tasks. This led companies to transition away from vector machine designs and focus on less specialized standard computers for their flexibility and cost. While the industry lost interest in vector machines, the technology had a resurgence due to video games. One of the key operations of video games is frequent updating of the display, i.e. involving the iteration across the individual pixels of the screen. Since a software pixel is simply a vector of 3 colors, and even in the 90s one could have hundreds of thousands of pixels on a display, these computations were an obvious opportunity for vectorization. In 1999, Intel introduced standard SIMD extensions, or SSE. The earliest generation of SSE had 128-bit registers, allowing for 4 concurrent operations at single precision. Since the application was gaming and graphics focused, there was no double precision support. Quickly, however, the scientific community realized that this technology was very useful for scientific applications. Since most scientific software relies on double precision computations, Intel was incentivized to introduce double precision support in SSE2. Then further generations of SSE continued to add further operations and functionality. Intel later introduced Advanced Vector Extensions, or AVX, in 2008, with hardware support in 2011, which extended the vector capabilities of modern CPUs with 256-bit registers, giving 4 concurrent double precision operations. Later, AVX2 added further integer operation support. However, in 2016, AVX 512 was announced, though hardware support continues to be uneven in 2025. This brought about 512-bit registers, i.e. the length of a cache line for x86 architectures, allowing for 8 concurrent double precision operations. As x86 machine cache lines are all based around 512 bits, further expansion in vector length is unlikely for these machines. On ARM-based machines, vector lengths up to 2048 bits are supported at the specification level, though in hardware these are managed through 128-bit registers. Though vector compute units have gained functionality through larger registers, challenges remain. For example, they typically run at reduced clock speeds. The actual hardware produces substantially more heat than the typical ALU due to the dense packing of the compute units and focus on computation primarily in that region of the silicon. When the vector units run very hot, the computer downclocks the CPU, and this behavior has led to some underwhelming implementations of vector computing in the past. Therefore, the performance of vector compute units can face a tension between their increased throughput but reduced speed. Beyond AVX, AMX, or Advanced Matrix Extensions, introduces vectorization concepts for small matrices at single precision. Such extensions are commonplace even in 2025 in an unexpected place, phones, since these represent tightly coupled coordination between hardware designers and software vendors. If history is any indicator, we predict the next generation of AMX2 to support double precision. Much like SSE was driven by the needs of the video game industry, AMX is driven by demands from the machine learning community. What distinguishes the current trend is the reliance of machine learning on low precision, often novel data types, making the translation to scientific computing more tenuous. In summary, vectorization is extremely useful for scientific applications, though sometimes quite challenging for the hardware design and the programmer. To enable vectorization, we should keep in mind some limitations. For example, if statements introduce control flow branches, which restrict the ability of the compiler to automatically generate vectorized machine code. Similarly, we should prefer contiguous data layout and accesses. In the simplest case, we rely on the compiler to perform the vectorizing transformation, so it is very good practice to pass appropriate flags, for example the march flag, to exploit the properties of your specific machine for your specific problem. Likewise, it is often worth considering whether a particular CPU provides appropriate hardware support for your problem. Often this translates to using newer chips for larger vector operations. Finally, there are some notable distinctions between vectorization and other concepts. For instance, modern CPUs support multi-core computations, which are not the same as vectorization. Vectorization is SIMD. Likewise, it is worth noting that GPUs share a historical lineage, i.e. they also implement SIMD ideas, even though they call it single instruction multiple thread. While their implementation is distinct, codes that are well suited for vector compute units also do well with GPUs. Thank you very much for listening, and I will see you in another lecture.